Hello my dear students, today we are going to start with a new topic. So first of all we will see the definition of similar matrices. So two square matrices A and B of same order, it is important. So whenever you are having two matrices of same order, then they are said to be similar if we are able to find if there exists a non-singular matrix P actually, if there exists a non-singular matrix P such that you should be able to write A in the form of P inverse BP, or you should be able to write B in the form of P inverse AP. I hope you are getting my point. If I want to give one example, suppose we talk about the matrix A is equal to 1, 2, 3, 4. Now how can I write it? This matrix can be written as A is equal to, or I can say 1, 2, 3, 4 is equal to 1, 0, 0, 1, which is the identity matrix inverse, again 1, 2, 3, 4, and again 1, 0, 0, 1 over here. So how I have written this matrix A? I have written this matrix A as, now this is the identity matrix, so I inverse, again it is A and it is I. Is that okay? So I have found out a matrix, a non-singular matrix I is non-singular, right? Because determinant is 1, which is non-zero. So I have found out a non-singular matrix I such that A can be written as I inverse AI. So what does it mean? This A is similar to A. Is that okay? So that is our first note. A matrix, a square matrix is always similar to what? Itself. Now suppose there are two different matrices A and B. Now how to say that they are similar? So they will be similar if we are able to find a non-singular matrix P such that you should be able to write A as this product of three matrices P inverse B P, or you should be able to write B as P inverse AP. Okay, if one holds, the other is obviously going to hold. So the meaning of these two statements is one and the same. You will say how? Because if I am writing A as P inverse BP, and if I pre-multiply and post-multiply by P, what you are going to get? So if I pre-multiply by P and post-multiply by P inverse, I will get PA P inverse will be equal to P inverse BP P inverse, but this P inverse will be I, since P is a non-singular matrix. So therefore we will get B is equal to PA P inverse, and which is nothing but what? It can be written as P inverse whole inverse A P inverse. And the role of, now you can see, if I replace this P inverse by P again, what you are going to get? P inverse A, okay, and which is same as this, isn't it? So my non-singular matrix in this case is nothing but P inverse. Since P is non-singular, P inverse is also non-singular. So my point is, this statement and this statement is one and the same. Ultimate aim is to get a non-singular matrix P such that this is satisfied. Okay, so once this is satisfied, this will be also satisfied, but for this P is equal to what? This whatever matrix we obtained here, where is that? Here. Okay, त्याचा inverse फक्त इथे येणार, isn't it? Okay, if you want you can use some different notations. I will go for P1 if you want, where P1 is nothing but what? P inverse, right? So you can see that B can be written as P1 inverse AP1, isn't it? And that P1 is non-singular only because P is non-singular, so therefore P inverse is also non-singular, so therefore this holds. So whenever this is holding, this is also holding, and whenever this will hold, this will also hold. So saying this thing and this thing is one and the same. Okay, so to sum it up, so two matrices A and B are said to be similar if we are able to find a non-singular matrix P such that either this holds or this holds. Okay, so the other thing is, if A is similar to B, then B is similar to A, isn't it? It is very simple and clear, because if this is holding, then this also holds. Is that fine? So if A is similar to B, then B is also going to be similar to A. I mean, it is the similarity satisfies the symmetric property. The first note tells us that the similarity of matrices satisfies the reflexive property, and this tells us that it satisfies the symmetric property. Definitely you can think whether it is transitive or not. What do you feel? Will the similarity of matrices be transitive? Let us try it. So I'll say let A be similar to B. This notation I will use for similar matrices, and I'll say let B be similar to C. So A is similar to B means what? There will exist some non-singular matrix P such that A will be equal to P inverse BP. Now since B is similar to C, again there will exist some non-singular matrix P1, I will say, such that B will be equal to P1 inverse C P1. Now we have to prove that, or we have to think that whether we will be able to find a non-singular matrix some P2 such that A should be equal to what? P2 inverse C P2. If this happens, then we will say that A is similar to C. So let us guess that matrix. So definitely I will start from the right hand side. I will say P2 inverse C P2. So you have to choose your P2 in such a way that you are going to get the left hand side, that is our A. Okay, and definitely we have to use this two equations in order to get that A. So my ultimate choice is, you can see the neighboring matrix of C is P1 from the right hand side obviously. So over here also I want P1. So I will choose my P2 to be some P1 first of all. So I'll get CP1, and on the left hand side of C I want P1 inverse. So I want somewhat like this, P1 inverse C P1, right? Then I will get B, this is my B, and to the neighborhood of B I want P inverse on this side, and on this side I want P. So over here I want P, and over here I want P inverse, so that I will get A. So what should be my choice of P2 then? So my choice of P2 is going to be P1P. So if I choose my, I'll say choose P2 is equal to P1P. Now note, since P1 and P are non-singular, this P2 is also going to be non-singular, isn't it? Because determinant of P2 will be determinant of P1 multiplied by determinant of P. But determinant of P1 and P both are non-zero. So therefore determinant of P2 will be also non-zero, and it will be also non-singular. Now let us try to do the calculation. So if I put my P2, it will be P1 P inverse C, and my P2 is P1P. Now you know AB inverse is B inverse A inverse, so that property can be applied. So I'll get P inverse P1 inverse C P1P, but this P1 C P1 is B actually, so this will be equal to P inverse BP, and P inverse BP is nothing but A, and that is our exactly the left hand side. So similarity of matrices is transitive as well. That is our third note. Now let us go for theory question number 3. So let A be a n cross n real matrix. Then we have to show that characteristic polynomial of A is equal to characteristic polynomial of A transpose. A very interesting result. Actually I have given this for homework, but over here we will prove it. So I am not going to go in details, just I will go on explaining. Then we have to prove that characteristic polynomial of B is equal to characteristic polynomial of A for any matrix B similar to A. So in other words, if we are having two similar matrices, then the characteristic polynomial is same, a very strong result. Okay. So over here B is similar to A actually, and we have to show that characteristic polynomial of B is equal to characteristic polynomial of A. The third part is little bit lengthy, and that we will see afterwards, and this third part requires this theorem also. Okay, that we will see afterwards. So let us go for the first part. So I'll say let A be a n cross n real matrix to show characteristic polynomial of A is equal to characteristic polynomial of A transpose. So characteristic polynomial of A is given by what? Determinant of xi minus A, and characteristic polynomial of A transpose is given by determinant of xi minus A transpose. and so therefore we have to show that these two things are equal. So what I will do is I am going to use some notation for a11, a12 and so on. Then we will find out the determinant. So I have used this notation for a. Now since we want a transpose also, so I will find out a transpose. So see the notation properly, it is a standard notation that we already know. So what will be a transpose? So this is our a transpose, rows will become columns, so a11, a12 up to a1n, a21, a22 up to a2n and so on. Now I want these two things, so I will find them separately. So what will be my determinant of xi minus a? Each element in the matrix will be multiplied by minus sign, and diagonally we are going to add x. So therefore we will get this. Okay, so you can see each element is multiplied by minus sign and diagonally I am adding x. So this is our determinant of xi minus a. What about determinant of xi minus a transpose? Same thing, we will multiply each matrix by minus each element of a matrix by minus sign, and diagonally we are going to add x. So you can see this. So I have taken a transpose of 1, they are not same yet. So I have taken this transpose of 1 actually, because you can see that this entry and this entry is different. So by taking transpose of 1 you will get this determinant of xi minus a transpose, and you can see that now these two are equal. Okay, so from 2 and 3 both are equal, as but determinant of a is always equal to, in general, determinant of b is equal to determinant of b transpose. So that property use. So therefore determinant of xi minus a transpose will be determinant of xi minus a. जर b च्या ऐवजी xi minus a टाकला तर तुमच्या लक्षात येईल. So I'll get this, and therefore determinant of xi minus a is equal to determinant of xi minus a transpose, and therefore the characteristic polynomial of a is equal to characteristic polynomial of a transpose. Now we'll go for part b. So we have to show that characteristic polynomial of b is equal to characteristic polynomial of a for any matrix b similar to a. So since b is similar to a, what will happen? So that is what we have to show, determinant of xi minus b is equal to determinant of xi minus a, because what will be characteristic polynomial of b? It will be determinant of xi minus b, and characteristic polynomial of a will be determinant of xi minus a. So we have to show that these two things are equal. But since b is similar to a, therefore what will happen? As b is similar to a, there will exist a non-singular matrix P such that this b will be equal to P inverse AP, right? So since now we have the value of b, what we have to show? We have to show that this determinant of xi minus b is nothing but P inverse AP is equal to determinant of xi minus a. Okay, so I will start with the left hand side and I will show that it is equal to right hand side. Now just note one thing, how can I write I can be written as P inverse P. Now there are two ways, I can be written as P inverse also and P inverse P, but note we are going to use P inverse P, because if you see this term properly, the P inverse is on the left hand side over here. Okay, so therefore we will use this and not this. Okay, so I will consider left hand side, so I will say consider LHS, that is determinant of xi minus P inverse AP, which is further equal to determinant of x, and the adjustment is P inverse P minus P inverse AP. Now since this x is a scalar, it can be shifted anywhere. This can be written as determinant of P inverse xp minus P inverse AP. Now since we have to approach to determinant of xi minus a, this can be further written as determinant of, I will take P inverse common from the left hand side and P common from the right hand side. So what will be left out inside? xi minus a, and out is P. You just cross verify it, you will understand it. So Now one famous property we have to use. What is determinant of AB? It is determinant of A multiplied by determinant of B. So this will be equal to directly from here to here. Now I said about this property is equal to determinant of A multiplied by determinant of B, but note this property is also true for 3 matrices. I mean, if you are having 3 matrices, then determinant of ABC will be equal to what? Determinant of A multiplied by determinant of B and multiplied by determinant of C. Over here the 3 matrices are involved. This is 1, this is 2nd, and this is 3rd. Okay, so the property can be used. So therefore we will get determinant of P inverse multiplied by determinant of xi minus A multiplied by determinant of P. Now since all are real numbers, so this real number I will shift over here. So this is equal to determinant of P inverse multiplied by determinant of P multiplied by determinant of xi minus A. So we got determinant of xi minus A in picture. So now the question is, what about this? So again we have to use the same property, but now for the 2 matrices and in the reverse way. We are having determinant of P inverse multiplied by determinant of P. So in the reverse way it will be determinant of P inverse P, right, multiplied by determinant of xi minus A, but P inverse P is I, and you know determinant of I is 1, so this will be exactly equal to determinant of xi minus A, and that is nothing but my right hand side, and therefore we will say this A is similar to what? B. Sorry, therefore we will say the characteristic polynomial of B is equal to characteristic polynomial of A, where this B was similar to A. So now let us check it. So over here as B is similar to A, so there exists non-singular matrix P such that this has happened, such that B is equal to P inverse AP. So I have considered the left hand side of this determinant of xi minus B, but B is P inverse AP. So B ची किंमत टाकली, मग I ची ॲडजस्टमेंट केलेली आहे P inverse P, जसं मी तुम्हाला सांगितलं. Then this adjustment of this scalar can be shifted anywhere. Then the P inverse from the left hand side and P from the right hand side has been taken common. Then the property has been used. Again the determinant of P has been shifted. You will get determinant of I over here, and that's it, determinant of xi minus A, and this is our right hand side, and that is what we wanted to prove.